In this video lesson we're going to learn how a dynamical system can be modeled and simulated in the ISMA environment. To get started, we have a simple pendulum, that is, a bulb of mass m attached to a hinge where a massless and stretchable string, the string length L, is sufficient for the bulb to be modeled as a point mass. The bulb swings back and forth due to the gravity of Earth, whose field is uniform in the area of interest, and due to the mechanical energy of the bulb. The system is in a perfect vacuum, so there is no air drag at all, which would otherwise slow down the bulb. Also, we neglect the friction in the hinge. The two previous assumptions result in a pendulum swinging forever, since the bulb never loses its total mechanical energy. Let us put the hinge into the origin of a Cartesian coordinate system. Let alpha be the angle between the string and the vertical axis, as shown in this sketch. There are two forces acting upon the bulb: the gravity force, always pointing downwards, and the tension in the string directed from the bulb to the hinge along the string. You should know the differential equation modeling the system from the course of physics at school. As you might have noticed, it doesn't contain the mass of the bulb. It got cancelled during the derivation of the equation, so the behavior of this particular pendulum does not depend on its mass at all. Apart from the differential equation, we need to provide some additional information. Specify the initial conditions for alpha and its first derivative, since we have a differential equation of order 2. For the sake of convenience, let us add the equations mapping the model outputs, the angle alpha and its derivative, onto the Cartesian coordinate system. Now, when the mathematical model is ready, let us proceed to the computer modeling phase. Since ISMA supports only modes defined by explicit differential algebraic systems of equations without derivatives of order greater than 1, we have to rearrange the problem description in the way shown on the left half of the slide. Here we explicitly define two state variables, alpha and omega, and also transform the rest accordingly. First of all, we define constants. A constant can be described by the keyword const followed by the name of the constant, which is L, the equals sign, the value we want to assign to this constant, in this case 1 meter, and a semicolon. Since ISMA supports comments, we can add one in order to improve the readability of the model. The G constant is already embedded in the environment, so we don't have to declare it. Along with line comments, ISMA supports block comments. A differential equation in ISMA is defined in a way similar to how mathematicians do it. We write the variable that is differentiated followed by the apostrophe, the equals sign, and its right-hand side. Note that in ISMA you don't have to declare variables explicitly. The initial condition for a differential equation can be specified anywhere, though it makes sense to do it right after the declaration. The other differential equation is described in the same way. Since we have not specified the initial condition, it is implicitly assigned 0. And here you can see the so-called output equations for x, y, vx, and vy. In order to simulate a model in ISMA, you need to press the green triangle first, which opens up the simulation settings window. Here we leave everything as it is, but maybe employ a smaller step size. After pressing the Run Simulation button and the simulation run is complete, you can see the simulation results by pressing here. You need to select the variables you want to see the plots of, and here you go.